The hottest topic in AI right now is using it to accelerate software and development. Coding copilots and agents like Claude Code, Windsurf, and Cursor, these are all becoming household names and fundamentally changing the way that software engineers approach their workflows. Adoption of these tools has been through the roof. Stack Overflow found that 80% of developers are using AI tools, with over half of them using them on a daily basis. More recently, Google found that 90% of developers are using AI at work. And studies on productivity gains for these tools are also huge, indicating that coding efficiency can be up as much as 50% when using AI-assisted development tools. I think we've all been getting pretty used to the stories of how powerful and incredible these tools are in practice. They're able to one-shot entire applications on their own. Here's an example from the GPT-5 launch where it created this entire web game from only a single user prompt. And there's countless other more practical examples of AI in action as well. Finding bugs, fixing security vulnerabilities, and driving entire refactors on its own. And yet, when you try to leverage these tools for data science tasks, something disappointing happens. Here I've just loaded some 2D data into a notebook. For reference, I've also put up a scatter plot so you can actually look at it. And I'm just going to prompt Claude Code to make a model that predicts y from x. And before I do that, you can already get some sense just from looking at this data of what kind of model you're going to want it to produce. There's clearly some sort of bimodality going on here, so I'd say it's table stakes that any model should leverage that bimodality somehow. But guess what Claude Code does? In this case, it literally just gave us a linear regression and called it a day. And this is not an isolated example. I got the same result when trying different models, when trying Cursor, GitHub Copilot, all of these tools. And in my opinion, this is pretty terrible. I don't think any reasonable person would say that this is good data scientist. Even the most novel of data scientists could do a better job here, develop a better model. And this is also an incredibly simple task. It's almost trivial. And so you can only imagine how poor a lot of these coding copilots are when you extend them to any even vaguely more complicated task, more resembling what data scientists are actually working on. The simple truth is that the current frontier of these coding tools are just not capable of doing real data science. Data scientists deserve better than this. My name is Jamie, and this observation is what inspired my co-founder and I to launch Sphinx AI earlier this year, where we're building agents that don't suck at data science and are helping real data scientists accelerate their workflows immensely, just as Cursor has done for software engineers. At the end of this talk, I'll share more about Sphinx and some of the features that make it so useful. But mainly in this talk, I want to explore in greater depth some of the shortcomings that coding agents have when it comes to data science right now, and why we so strongly believe it was necessary to build a dedicated data science agent in the first place. The first challenge here is that software engineering is just fundamentally different from data science. If we look at a software engineering workflow, it's actually pretty simple for the most part. An engineer identifies what they want to build, they write some code to implement it, and then there's this very simple iteration loop to fix bugs until they have it working. That's pretty much all a coding agent is really doing under the hood, and this works pretty well for software engineering. But this really doesn't translate to data science at all. Here's the raw output that I got from Claude Code earlier, for that task from earlier. And to be honest, if we look at this code, for the most part, it's actually pretty good. It's free of bugs, it's well organized, and it's using a lot of external libraries correctly. But if you look at this notebook, you might notice something a little odd, which is that none of these cells were ever actually ran. And that's a little odd, isn't it? Because what's the point of operating in a Jupyter Notebook in the first place if you're not going to be working iteratively? There's no iteration going on here. There's no reasoning about intermediate outputs, and there's certainly, as a result, no real good data science going on. And this speaks to the fact that data science workflows are just fundamentally a lot more complex than they are for writing software, with constant iteration and introspection being an absolute necessity throughout this process. You gather some data to test a hypothesis, and you look at it to figure out how you need to prepare it. You write some models to analyze it, and you look at the results, see if they match your expectations or if there's something surprising going on. You debug results, you gather insights, and you write reports. And critically, throughout this entire process, you need to be constantly asking yourself if what you've done so far looks right to you, or if you need to go back to an earlier point. Maybe you need to gather more data. Maybe you need to try a different modeling approach. Maybe your hypothesis has been invalidated and you need to try something else. And ultimately, the difference between software engineering and data science is that whereas in software engineering, the code is sort of the goal at the end of the day, that's the real output. In data science, the code is really just a means to an end, with the real goal being to develop a better understanding of your data in the first place. This different workflow requires different tools, and of course it really goes without saying where we are, but Jupyter is the perfect tool to handle these iterative workflows in the first place. And for that reason, it's hard to imagine a data science agent existing without first-class support for Jupyter. This means not only being able to write and read notebook contents like we saw Claude Code doing earlier, but also being able to execute cells and look at the outputs of those executions. And we're talking about more than just notebooks here as well. Jupyter kernels provide an entire runtime environment that exists in parallel with the code. An agent needs to be able to understand that this environment exists and how it operates. It needs to be able to introspect this environment, inspecting variables and listing installed packages and seeing what versions of those packages are installed. And it needs tools to manage the environment as well, everything from installing new packages, running code directly against the kernel, or resetting the kernel altogether if it gets into a weird state. And without any of these capabilities, it's obvious that an agent would be operating with a major handicap. And so we consider integration with Jupyter to be one of the defining capabilities that an agent needs to have to be useful at data science. The second big shortcoming of coding agents for data science is that they just don't understand data. I'm going to take a step back here to talk a little bit more about how most agents work. The LLM at the core of an agent is essentially just a giant text-to-text engine, taking a bunch of text as input and outputting a bunch of text as its result. Where this gets interesting is that increasingly LLMs are able to take very large amounts of text as input, which provides an opportunity for us to pass a large amount of additional information as input. We call this the context window, and it's used extensively by agents today. A typical coding copilot might have its context window filled with all kinds of information and documents, like this can include code snippets, memories from past sessions, tool call outputs, system instructions. There's a lot of these examples. This all gets serialized into a single prompt that the LLM then ingests in order to make as informed a decision as possible. This approach has proven really powerful, and today it's one of the biggest ways to improve agent performance by just adding more to your context window. And especially by integrating with third-party tools through frameworks like MCP to add new context sources to models. Unfortunately, this approach of just dumping everything into the context window falls apart when dealing with data. And the problem is really just a simple matter of scale. LLM context windows really are big. Typically, they can handle the equivalent of several novels worth of context. But data is just bigger. Consider like the Lawman baseball database. This is a classic open database that contains complete information about every Major League Baseball game ever. If we consider just the batting data from this table, that gives us about 100,000 rows by 20 columns. That turns out to be about 15 megabytes or over 5 million tokens. Too big. And the problem's only going to get worse from here. Say we want to do a financial analysis on S&P 500 data for the past 20 years. That's about 2.5 million data points, about over 50 megabytes or over 10 million tokens. These data sets are already too big, and you can imagine how much worse the problem can get. Plenty of data sets are bigger, and plenty of analyses are going to involve multiple data sets. And so unfortunately, the classic agentic technique of just dumping everything into a context window to let a model sort it out clearly doesn't work for data. And there's a second, more subtle problem here as well. Here's the data from that bimodal modeling task that Claude failed at earlier. This is just a raw data frame in all its numerical glory. That's pretty representative of what a typical data set looks like. And like, if I just gave you this raw data and the same prompt from earlier, make a model that predicts y from x, and this is all you don't get to make any graphs, charts, or whatever, you just need to look at this raw data, and from that identify conclusions, that's clearly not a reasonable way to approach a data science problem. It's just not reasonable to go straight from this data to identify that there's a bimodality and that you need to end up with something like this. However, this problem gets much easier to reason about just as soon as we create an intermediate scatter plot of the data. This very simple graphing step in this case immediately reveals an enormous amount of information about the structure of the information we're dealing with, and from here that clustering step is actually pretty intuitive and easy. Unfortunately, this sort of exploratory step just simply isn't intuitive to today's coding agents because it doesn't have a strong equivalent in the software engineering world. And so we need to go out of our way to teach our data science agent to perform these kinds of intermediate exploratory steps. This process, of course, has a name, exploratory data analysis, and it's one of the richest, most important, and most difficult parts of data science today. There's a huge amount of different techniques that we need to teach our model to be able to handle. There's basic plotting techniques, like we just saw, in other words, looking at the damn data. There's algorithms like k-means and Gaussian mixture models for grouping data into discrete clusters. There's a whole gamut of work to do in preparing data for analysis in the first place, which though a lot of this can be very algorithmically simple, is also very error-prone and rote due to having to sort through things like mismatched columns and weird data formats. When dealing with higher dimension data, techniques like PCA and T-SNE can become very important to simplify the data into a format where it can even be visualized in the first place. For social applications and some geographic data, it's common to construct graphs of relationships between different data points in order for us to then perform analyses like detecting hub nodes and clusters. And if we're dealing with natural language data, like reviews for a product, it's common we might need to use AI-based techniques to transform this data into a format more suitable for traditional data analysis. Point is, there's an enormous amount of these techniques that a data scientist is using very commonly, and that our agent needs to be able to be familiar with so it can apply these techniques proactively as appropriate. This is a really hard problem for the agent, actually. We think this is probably the single hardest problem that a data science agent needs to reckon with. And to us, it's no wonder that coding copilots just don't really understand this step. And another major challenge in building a data science copilot lies in ensuring that analyses are verifiable and explainable. Again, this isn't really a challenge that software copilots have to grapple with. The reason being is that since software is generally just defined by its functionality, there's generally a pretty direct, simple way to verify that it does what it's supposed to do by just straightforward testing. Like if you use AI to generate an app from scratch, you can just manually test that it does what you're expecting. If you use AI to fix a bug, check the bug is fixed. If you're doing a big refactor, check that the test suite still passes. And if you're doing some sort of performance optimization, you can just check that performance has been improved as expected. And critically, none of these verification methods really involve looking at the code itself. This is kind of like the core thesis behind vibe coding, that it turns out software engineers are fairly okay with just sort of ignoring the code itself as long as it acts as expected. The trouble is, this doesn't apply to data science. Like imagine you had a tool, or say maybe a reporting employee, who would only give you direct answers to your data questions. You ask it to create a model that predicts some target value and it just gives you a direct function. You ask how much money you're making from a recent product purchase and it gives you an exact dollar amount. You ask who's going to win the Super Bowl and it just gives you a team. You ask if you should short a stock and it treats that as a yes or no question. And like, sure, all these outputs do technically answer the question asked, but they are sorely lacking in context. There's no evidence to back up these conclusions. There's no notebook that can be verified for correctness, and there's no visual aids to illustrate key insights. Like without context, we're not really doing data science. Like this is just sort of a question and answer bot, and I don't think anyone would take these answers seriously. And like, if this seems like a far-fetched vision, like, think again. The advent of reasoning models actually represents a very real threat that models are converging on these patterns. At first glance, reasoning models seem like something that should be helpful here. A reasoning model is essentially just an LLM that produces reasoning tokens as a way of enriching its context window before producing a final answer. These reasoning tokens give the model a chance to informally explore different ideas, kind of like thinking. And in general, we found that reasoning models do, in general, produce more accurate outputs. The problem is that reasoning tokens are fundamentally not output tokens, and they have some distinctly different properties that make them less useful here. The first problem is that models are trained to produce correct outputs and not necessarily correct reasoning. Anthropic recently found that reasoning models can produce outputs that do not logically follow from their reasoning, suggesting that these models have a bias against unintuitive, but nonetheless logically supported conclusions. And in these cases, relying on the reasoning trace can give an inaccurate sense of how a model reached its answer. For OpenAI models, the problem is even worse. They hide most of the reasoning from the user altogether. They're very transparent about why. They view this as sort of IP, and therefore they want to maintain a competitive edge. And so if you want to understand why an OpenAI reasoning model is doing what it's doing, good luck. The solution is very simple. We believe a data science agent just shouldn't rely on reasoning models. It should instead be prompted to create explicit thoughts that guide its reasoning as part of its output, and that these thoughts should be evaluated for correctness as part of the model training process, just like the whole rest of the output. But this represents just yet another departure from how most coding agents are designed, and so it just becomes one more reason why our data science agent needs to be a little bit different. To summarize, data science is a rich, complex, and demanding discipline. We think it's very distinct from software engineering, and it's a core belief of ours at Sphinx that data scientists deserve agents, copilots, and AI tools that are built by data scientists for data scientists, and not for software engineers. And that's why we built Sphinx, an agent from the ground up for data scientists that integrates directly with Jupyter Notebooks. Our main client plugs directly into VS Code's Jupyter extension and provides an interface that will be very familiar to anyone who has tried using coding copilots before, except that Sphinx is an expert in assisting with data science tasks. Let's look at it in action. Here's that same setup from the start of this talk, where we're seeding a notebook with some data and asking Sphinx to make a model from that data. Sphinx has been trained to approach data science problems much like a human would, and that means starting with exploratory data analysis, rather than jumping straight into blind modeling like Claude did. Here, Sphinx is going to write some code with matplotlib to produce a scatter plot of the data. Sphinx can run the cell and look at the output to decide what to do next. Under the hood, we're using multimodal models to power Sphinx, meaning that it's capable of ingesting images like these charts and graphs just as easily as text. And thanks to that, we can see from Sphinx's thought log that it's now recognized that it's dealing with bimodal data, and it needs to plan the rest of its work accordingly. From here, Sphinx is ready to proceed with modeling, and it's pretty straightforward. It's decided to use Gaussian mixture models as a clustering algorithm to separate the data into clusters and independently fit regressions to them. Judging from this graph, I'd say it's done a pretty good job in this case. Sphinx's defining ability is really its ability to immediately execute the code that it writes, and this has led to some pretty interesting emergent behavior. For instance, I mentioned earlier that one of the hardest ways to improve agents is giving them access to more context, and to that end, Anthropic recently released the Model Context Protocol, MCP, which is a way for agents to access arbitrary data from APIs like Slack, Google, and GitHub. MCP isn't perfect. Servers need to be very manually implemented and configured, and there's a lot of headaches around things like authentication with MCP right now. Nonetheless, it's been hugely impactful in terms of making agents more powerful and able to bring in more data sources. Thing is, we found Sphinx doesn't really need MCP for surprising reasons. If we ask Sphinx to perform a task that would typically involve accessing a third-party API, like say loading some data from Yahoo Finance, well then sure, we could have solved this by configuring a Yahoo Finance MCP server and just have Sphinx access the data that way. But because Sphinx can write and execute arbitrary code, we can just access the Yahoo Finance API directly. This is far simpler than using MCP. This works out of the box with Sphinx and doesn't require any manual configuration, and even better, we're loading this data not only into the model's context window, but also into the underlying Jupyter kernel state, opening the window for us to do further data analysis on this as opposed to just letting the model sort it out. And the reason this works is because it turns out LLMs are already pretty good at using a lot of common APIs out of the box. We found Sphinx can load data from pretty much any public source, and it can also figure out how to access private data sources like Snowflake and Databricks, just so long as you give it some information on where to find credentials. The execution-centric nature of Sphinx has also inspired some other really awesome features that help Sphinx drive analyses efficiently. One obvious one is that Sphinx can fix errors when cells don't run successfully. Here's an example where Sphinx hit an error because it used the wrong casing for a column name. Sphinx was able to fix the cell and rerun it successfully. We also recognize that some users may be uncomfortable with the idea of an agent running code autonomously, and we take that very seriously. To that, we've implemented a system of guardrails, where Sphinx can be configured to ask for permission before running certain types of code cell, like file write operations and package installations. And a personal favorite of mine, Sphinx can also detect when a cell is hanging or running unnecessarily slowly and automatically interrupt execution to optimize it before trying again. Here's an example where Sphinx was using an exact nearest neighbors algorithm for a data set that turned out to be too large for that algorithm, and it decided to rewrite that cell to substitute in an approximate algorithm. I'd love to keep talking about Sphinx, but that's all the time I have. If you're interested in learning more about Sphinx or seeing a demo of it in action, taking on a more complicated task than what we showed here, we have a booth out in the expo hall. We'll be there through the end of the day. Otherwise, I have the next few minutes to answer any questions you might have. Thank you.